So now that we know how to do triple integrals, the next step is to then think about possibly changing the coordinate systems from either rectangular to cylindrical or rectangular to spherical in order to more easily complete the triple integral. We would only talk about cylindrical and spherical coordinates when it comes to triple integrals because of the number of variables. Polar coordinates would not be an option for triple integrals. In that polar coordinates is a two-dimensional measurement. Cylindrical and spherical coordinates are three-dimensional coordinate systems. And when you integrate with a triple integral, you're integrating over a volume, and volume is a three-dimensional measurement, so these things have to live in three dimensions. So polar coordinates would not be an option. All right, so when would we do cylindrical coordinates? Well, it depends on what we're integrating over. Remember, you're integrating over a volume, which we call a box, okay? You're integrating over that box. What we want is that box to have a particular shape. If our box is a more traditional box that looks like this, maybe it's best to stay in rectangular coordinates. However, if our box has a more cylindrical shape to it, and cylindrical coordinates, remember, is circular in the xy direction but linear in the z direction, then maybe cylindrical coordinates would be a good idea. You know, this will typically happen when you have a lot of x squared plus y squared expressions in your functions. Probably cylindrical coordinates might not be bad. Remember, this is the conversion that we use for cylindrical coordinates. X is r cosine theta, y is r sine theta, and z stays z. And we have this rotation in the xy direction, but a linear value in the z direction. That's how we get our point. So if our volume that we're integrating over is a box that's more similar to a cylinder, then maybe we want to use cylindric coordinates. Remember, when we do this, what we do is we look at these little cubes inside this box, and we add these cubes up. This is a really bad set of cubes. Let's get a better cube here, right? So we add these cubes inside the box, and we stack the cubes up to fill up the box, and we add up a stack of cubes. The difference would be if we do it in cylindrical coordinates, our cube won't look like a standard cube that we're adding up, right? This is the mini cube that's inside of this box here. Instead, the cube is going to be based off of a polar sector. So if this measurement is done with polar coordinates, the idea would be the base of the cube would look more like this, and then we would have our cube created linearly from there. And so this is going to be what these cubes look like, and we're going to stack one on top of the other. And so that idea of our cube, our base element to create this volume, changing a little bit, well, then we have to change our formulas a little bit. So think about it. How do we find the volume of one of these stacks? We take the volume of one of the cubes and add it or multiply it times the height of the stack. This represented the volume of one of the cubes. This was dV. Well, if we do it in terms of cylindrical coordinates, we now need to find the volume of one of these polar cubes, okay? Remember, the base is kind of a polar sector and then linearly in the z direction. And so the way we find the volume of one of those polar cubes is essentially to use this formula of r dz dr d theta. It's the area of the base times the height. We already saw that the area of the base is r dr d theta. So then we just have to multiply it by the change in the height, which is dz. So that's where the r dz dr d theta comes from. That's the volume of the base times the height of the stack, which goes up to the function value. So that's this. So we have dv times the function value. But the function has to be converted over to cylindric coordinates. So x is r cosine theta, y is r sine theta, and z stays z. And then the limits of integration have to follow suit as well. So in this case, z would be between these functions of r and theta. Then r would be between these functions of theta, and then theta is between these two constants. The best way to do this, I think, is to always do z first as your variable. It's easier to do z first in most examples and then do dr and d theta next, and that order doesn't really matter because once we get past z, we're just dr and d theta. We're basically back to the setup that we would have in polar coordinates. We only have two integrals to go. We only have two variables, r and theta. And remember, cylindrical coordinates is basically polar coordinates dumped in 3 dimensions. So if we take care of the z first, then we go back to what we've already learned, which is, double integrals in polar coordinates. So here's a prime question for converting to cylindrical coordinates. In deciding should I switch to cylindrical coordinates for a given problem, in this case it tells you to do that, but if you're looking at a problem, you're asking yourself, which is the best way to solve this triple integral? Do I leave it as x's and y's? Do I convert to cylindrical? Eventually, do we convert to spherical? It's not as much the function that you're integrating here as the box that you're integrating over is the deciding factor. So this box is telling me that x is between -2 and 2, y is between these two square roots, and then z is between these two values. And what would be best is if we sketch this out to really see what's happening here. I'm going to ignore the z for a second. I'm going to look at this. Okay? If I just look at the x's and y's, I'm going to figure out what's happening in the xy direction first, and then I'm going to dump that into 3 dimensions and deal with the z next. So the idea here is y is between the negative square root of 4 minus x squared and positive square root of 4 minus x squared. Well, you should recognize that those two square roots are basically the top and bottom half of a circle radius 2. If I looked at, say, y equals 4, or square root of 4 minus x squared, so the positive square root, and I square both sides, and then I move the x squared over, I have that. That's a circle radius 2, centered at the origin. But it's only the top half of the circle because it's only the positive square root. The negative square root would be the bottom half. So you got to be able to see that when you're looking at these functions. What are you looking at? So I have this top half of the circle. I have this bottom half of the circle. That's what y is between. Okay. The x's range from -2 to 2. So the x's range from here to here. So basically, I'm talking about this whole circle. That's what these two inequalities are representative of. Then I need to throw that into 3-dimensional space. So then what do I have? Well, I have a circle radius 2 in the xy direction. That's this. So radius 2, so 2, 2, this will go back, this will go this way. And then the z's are between these two functions. I don't really need to know what those functions are. I just know one of them is on top, that's the 2, and the other one is on bottom. Okay? And so I'm looking at these two functions here. I got to find the volume between those two things, but only in this circular area below it. So if I was to push this circle up through those two surfaces, right? There's these two surfaces here, and look at the space in between. I know this is starting to get messy. Let's try that again. I have this circular thing happening in the xy. I have this one surface z, and I have this other surface z, okay? 2 being the one on top, square root of x squared plus y squared being the one on bottom, okay? And so I want to find the volume in between those two based off of just this circular fashion in between. It's not a great picture, but I think it gets the point across of how we're going to look at the volume we're integrating over. This would work really well in a cylindrical coordinate system, which is why we're going to convert. So what we want to do is we want to convert a couple of things. We want to convert, and we'll draw that a little smaller. There we go. Okay. We want to convert the function to cylindrical coordinates. We want to convert this dv to cylindrical coordinates, and then we have to convert the volume itself to cylindrical coordinates. So the function is easy. This x squared plus y squared function here converts over to just r squared in cylindrical coordinates. It's one of our formulas. dv for the conversion is r dz dr d theta. That's standard for cylindrical coordinates. That's the volume of one of those little polar boxes that we're going to use to fill up this space in here. And then it's a matter of converting this region over to cylindrical coordinates. Well, the z, okay, z is between 2, which no matter what coordinate system is, 2 is a constant, okay, and the square root of x squared plus y squared. Well, that converted into polar coordinates is the square root of r squared, or just r, okay? So that's that conversion. And then as far as x and y goes, remember, this is what we have in terms of x and y. So what's r between and what's theta between, right? R is this distance, theta is the rotation. So r is between 0 and 2, and theta is between 0 and 2 pi. So here's your limits of integration. This is just going to be r itself, okay? This is the function we're going to integrate, and this is the differential for this integral. Put it all together, we got our triple integral. Then we need to solve it and get our answer. This is easier because we've already covered polar coordinate integration. And this part of the process is essentially polar coordinate integration. We have this extra integral of this extra variable z's to contend with. But other than that, you know, you're really looking a lot of what we did back in polar coordinates. So let's finish off this integral. Okay, so this triple integral of x squared plus y squared with respect to the volume over the region that we were talking about will be converted to the triple integral in cylindrical coordinates of r squared, that's this function, times the differential now being r dz dr d theta, and that order is predicated on the intervals that we came up with, such that z was between r and 2, and that's why z has to come first, because there's a function here. R and theta, the order we can mess around with, because they were between constants. R was between 0 and 2, and theta was between 0 and 2 pi. I'll just leave it in this order since that's how I wrote it down. But we could rearrange this order and simply rearrange these two integrals since everything's constants there. But z does have to come first because of the function value, the fact that there's an r here. So this is the integral we have to do. It's not a very difficult integral. It's easier than if we left it as is, right? And so we have the integral from 0 to 2 pi, that's going to sit there. 0 to 2, that's going to sit there. This is going to be r cubed. If we integrate that with respect to z, we're going to get r cubed z, where z went between r and 2. We still have to deal with dr and d theta. So then we're going to plug in 2 and plug in r for z. And we're going to get 0 to 2 pi still, 0 to 2. We're going to have r cubed times 2, so 2r cubed. And then we're going to have an r cubed times an r, so it'll be an r to the 4th. And we're going to integrate that with respect to r. And then d theta after that. So now we go with respect to r. Well, these are two easy integrals with respect to r. So we're going to have still the integral from 0 to 2 pi. We haven't touched that yet. 2r cubed would be r to the 4th over 2. And r to the 4th would be r to the 5th over 5. And that's between 0 and 2. We still have to do d theta. So then we'll plug in 2 for r and 0 for r. And so we end up with 0 to 2 pi. We're going to have plug in 2 to the 4th is 16 over 2 is 8, minus 32 over 5. That's 2 to the 5th. If we plug in 0, we get 0, so we just have that constant. We can simplify that a little bit. But then we integrate that with respect to theta. Well, there's no more thetas, it's just a constant, so it's just going to be this times theta. So if we multiply this by 5 over 5, you're going to get 40 over 5 minus 32 over 5, which gives me 8 over 5, times theta, where theta goes from 0 to 2 pi. So then I'll plug in 2 pi, and I'm going to get 16 pi over 5. If I plug in 0, I get 0. So 16 pi over 5 would be the answer for that triple integral. of integrating this function over that region we discussed, but switching it into cylindrical coordinates. Okay, so here's another example. We want to use the triple integral to determine the volume of a region below z equals 6 minus x and above z equals negative square root of 4x squared plus 4y squared inside the cylinder x squared plus y squared equals 3 when x is less than 0. There's a lot there, so let's look at it. Z equals 6 minus x. That's essentially the top here of this picture. It's a plane, okay? It's a plane. There's no y value there. So you would think of this as a line where the y value could be anything, where we talked about these cylindric surfaces where one variable is missing. So this is the top, okay? On the bottom, we have this function here, this negative square root of 4x squared plus y squared. So it's this cone-like figure here, okay, on the bottom. That's your z's going this direction. The cylinder, x squared plus y squared equals 3, is this circular pattern that we have here. You know, that it would basically be, if you look at it just in terms of the x and y's, is this circle radius root 3, but since x is less than or equal to 0, it's only this half of the circle. So that half of the circle is in the xy plane. That's why this here is just a half a circle or half a cylinder here. So you put all that together, this is the figure that you get. The z's are between, again, this plane and this cone, okay? And the outside of it is this cylinder, this circle, okay? But only half of the circle because the x value is less than 0. It's a circle radius root 3 because this is your radius, and that's r squared, so root 3. So if we want to find this volume, okay, we would just do the integral of this region with respect to the volume. There's no function to integrate over in this case, okay? The z's, the x's, and y's will create the volume themselves. So the region that we're integrating over creates the volume itself. So this is how we're going to calculate the volume. We'd have to define the region based off of this picture and integrate it with respect to that volume. All right. Now, we could do this in terms of x, y, and z. It's going to be kind of messy. Z would be between this function and this function. We see the bottom is the cone, the top is the plane. Okay? And then x and y can be done here. We could say y is this way, and it would be between this curve and this curve, which would be 2 square roots. And then x is between 0 or negative root 3 and 0. Or we could do the opposite way. We could say x goes this way and define it by this curve, and then y goes this way. But there's going to be a lot of roots involved there. Okay, z's between roots, y would be between roots, x would be between constants. But looking at this picture, this looks a lot like a cylinder. Okay, so why don't we switch this to cylindrical coordinates? So as far as the z's go, z is still going to be between these two surfaces, but we would convert these surfaces into cylindrical coordinates. So this 4x squared plus 4y squared, if you factor the 4 out, it would be x squared plus y squared, which is r squared. So this will be the square root of 4r squared, or 2r. So that's that with a negative, so negative 2r. On the other end, 6 minus x, well, x is r cosine theta, so z would be between 6 minus r cosine theta, and then on the bottom end, it's minus 2r. So we can do that easily. Then as far as the rest of it goes, r and theta will come from this picture. R, again, is the distance out from the origin, and that would be between 0 and the radius, which is root 3. And theta is this rotation this way, okay? And so it starts here and has to go to here. So this would be pi halves, okay? And then this would go to 3 pi halves to give us this half of the circle. So the rotation would be from pi halves to 3 pi halves. So it's easier to look at this in terms of cylindrical coordinates, a lot more constants going on here, than functions with these square roots in them. So I'm going to use cylindrical coordinates. So if I do my triple integral, I know my differential dv will convert to r dz dr d theta. I have to do z first because of the r's on the limits of integration. But as far as r and theta, the order really doesn't matter. We'll just do dr and then d theta. So then here's my intervals for z. Here are my intervals for r. Here are my intervals for theta. All right, so we're going to do our integration. So first we start with z. So we're going to integrate r dz, which just gives us rz. And z goes between our 6 minus r cosine theta and minus 2r. We plug each of those in for z. So r times this gives me 6r minus r squared cosine theta, and then r times minus 2r, and it's giving me 2r squared. I subtract that, so it's plus 2r squared. Now it comes time to integrate that with respect to r. Pretty easy. 6r goes to 3r squared. R squared is 1/3 r cubed, and 2r squared is 2/3 r cubed. Here, the cosine theta is a constant multiple in terms of r, so it just sits there, okay? And we're going to plug in square root of 3 for r, and then 0. Nice thing is when you plug in 0, you get 0 for each one of these. So it's really just square root of 3. Here, you're going to get square root of 3 squared times 3 is 9. Square root of 3 cubed times 1/3 gives me square root of 3. And square root of 3 times 2/3 cubed, or square root of 3 cubed times 2/3, I should say, is 2/3. 2 times square root of 3. And now we're going to integrate that with respect to theta, right? So 9 would be 9 theta. This would turn into minus square root of 3 sine theta. And then the last one here, switch the order up a little bit. This would be 2 square root of 3 theta, okay? So then theta goes between 3 pi halves and pi halves. And we'll plug that in for theta everywhere we want. And then pi halves as well. Subtract. This is what we get, 2/3, or 2 square root of 3 plus 2 plus square root of 3 pi. You can leave your answer like that. You know I prefer this answer. It's a more exact answer. But if you plug that in your calculator, it's about 42.6212 is what we can get. But nonetheless, the answer, I like this one better, would be here. And that would be integrating by switching to cylindrical coordinates. The next option is spherical coordinates. Now remember, we're integrating over a volume. This is still triple integrals we're going to be using here if we convert to spherical coordinates. So think about the box that you're integrating over. We have our traditional box or something like this type of box. Maybe these are functions and it's not as flat, but still it's more of a traditional box. We have our cylindrical box. And now we're saying we could also have a spherical box. And so depending on what region you're integrating your triple integral over, this box that you're integrating over, if it looks more like something like this, where it's more vertically and or horizontally simple kind of creation, or maybe it's circular in the xy but linear in the z direction, or in this case circular in all directions, you might want to change your coordinate system to fit the box that you're working with. So, again, how did we do this? What we did is we did it by a bunch of mini cubes. Right? These fill up this box with a bunch of mini cubes. We stack the cubes up over and over and over again. Volume of a stack. Add up all the stacks, you get your volume. Here, our cubes kind of emanated from the center, and they were these polar cubes that we were stacking up. Okay? And I don't know, that doesn't come across very well, but the cubes were just more like this. Let's see if I can do this time. Okay, they look more like that, and we would stack those up. But the same idea is you're going to fill this space up with these cubes that are stacked up, but they look a little different. Well, what about this? Well, same idea, but the stacking's not going to go vertical. What's going to happen is that we are circular in this direction, and we're circular in this direction. That's the sphere. So our cubes are going to not stack up vertically, but this measurement is also curved. So as we stack them, they're going to stack this way. And we're going to fill up the space like that with our cubes. Now, cube is used lightly. When I say cube, it really should be in quotes. I mean, these cubes are not necessarily cubes anymore. They're curved this way, and they're curved this way. Right, so there's a lot going on here. But nonetheless, if we could create our volume through those types of cubes, that would be spherical. So remember some of your spherical formulas. They were probably the more complicated ones: x, y, and z. Or if you want to go the other way, rho, tan theta, tan phi. So we got to think of, all right, well, what's the volume of one of these cubes going to look like? Because that's really the differential. That's the dV that we need to work with. So for cylindrical, we saw it was r dr d theta dz. That was the volume of one of those cylindrical cubes. So what's one of these spherical cubes going to look like? Well, the formula for one of those cubes is based off of all these distances. So you need this distance here, you need this distance here, this distance here. Through a little bit of trigonometry, we could come up with those values. But overall, the volume of that cube will be calculated using this. Okay, rho squared sine phi d rho. So the change in rho, the change in phi, the change in theta. So this is our new differential, right? That's our dV. So when it comes from taking our original integral, okay, and converting it over, we can convert the original integral over by converting the x, y's, and z's over using our formulas in our function. We can convert the differential over by using this formula, and then we convert the limits of integration as to say what's rho between, what's phi between, what's theta between, by looking at the different measurements. I'll tell you that when it comes to spherical coordinates, the only time you really want to change an integral over to spherical coordinates would be when you're integrating over a sphere or some part of a sphere. Spherical coordinates does not lend itself to very many boxes, okay? I mean, you can make a couple of different looking boxes kind of fit into cylindrical or fit into rectangular, but not a whole lot fits into spherical unless it's a sphere or some part of a sphere, a quarter of a sphere, half of a sphere, whatever. So you're not really going to see a ton of different examples that work well with spherical coordinates. I mean, you could force things to work into spherical coordinates, but that's not the whole point here. The point is to pick what's the easiest way to do a triple integral. So when you look at this example, this would be the typical example you do. It really isn't about this function so much. It's about the region we're integrating over. The box, and box is loosely being stated here, box is a sphere radius 1. So that's the region we want to integrate over. We want to integrate over this sphere that has a radius of 1. Okay? Now, we could do it in terms of z and x and y and stay in rectangular coordinates. That's going to be pretty difficult. There's going to be a lot of square roots, the top half of the sphere, the bottom half of the sphere, the y and the x. We can do it. It is definitely doable. But doing it in spherical coordinates is much simpler. Okay? So what do we have to do? We have to do three things. We have to convert this region that is defining the sphere from x, y's, and z's to rho and phi and thetas and figure out what all those are between. We need to convert this function to rhos and phi's and thetas, and the differential has to be converted over to rhos and phi's and thetas. Well, those two things are probably the easiest because you just use your formulas. So x squared plus y squared plus z squared, that equals rho squared. So this e to the x squared plus y squared plus z squared to the 3/2 as a function converts over to e to the rho squared to the 3/2. Well, power to a power is basically what this is. I would multiply those. So I would just get e to the rho cubed. And so that one's done. The differential, dv, we already said, should be rho squared sine phi d rho d phi d theta, and obviously this order will depend on, how we set this interval set up. Right? We may be forced to do it a particular order. All right, so we have all that, so then all we really need is to define the sphere. Well, rho is the radius of the sphere, okay? And so we go between 0 and 1. Theta is the rotation this way around the sphere and around the xy plane, okay? In which case we could say 0 to 2 pi. Or say that's theta, okay? Phi is the rotation off the positive z-axis. So this direction is my phi. And so to get the full sphere, we don't have to go 2 pi all the way around. We actually only have to go pi around that way. Because if you take this flat disk, which is what we created through these two things, and you flip it pi this way, okay? This end will flip this way. At the same time, this end is flipping this way, and it will carve out the entire sphere. So phi only has to go 0 to pi, okay? So that's all the pieces we need. We have our intervals for our integration, we have our function we're going to integrate, and we have our differential. Now in terms of all those things, these are all constants. So order actually doesn't matter at all. So if we just leave it d rho, d phi, d theta, or we want to switch it up to d theta, d rho, d phi, doesn't necessarily matter. So the triple integral will be this times this. So I have e to the rho cubed, rho squared, sine phi. I'm going to go d rho, d phi, d theta. And actually what you see here is since the intervals are constants, so 0 to 1 on the rho, phi would be the next one, 0 to pi, and theta would be 0 to 2 pi. Since everything in my intervals are constants, and these are multiplied together, we could split this into 3 separate triple integrals. Single variable triple integrals. That's one of the tricks we learned when it came to doing integration. If all your functions are products of single variables and your integration is happening with all constants, we can split this up. So that's how we're going to do it. So the 3 integrals we're going to split this into would be the integral from 0 to 2 pi of d theta, because there was no theta function, times the integral from 0 to pi of sine phi, d phi, and times the integral from 0 to 1 of e to the rho cubed times rho squared d rho. This one, super easy. This is just going to be theta between 0 and 2 pi times this one's going to be the integral of sine is negative cosine of phi between 0 and pi times, this one is a little more challenging but not bad. If you let u equal rho cubed, du would be 3 rho squared d rho. And I have the rho squared d rho, just not the 3, so I divide by 3. So this will become the integral of e to the u du over 3. And so that would just be e to the u over 3, u being rho cubed over 3, and that'll be between 0 and 1. So we still have these other two here. So this will be 2 pi. So plug in a pi and then plug in a 0. Cosine of pi is negative 1, so that becomes 1. Minus plug in 0, you're going to get 1. So you get plus 1. And then here I plug in 1 and 0. So I have 2 pi times 2 times e to the first over 3 minus e to the 0, which is 1 over 3. And so we could write this as 4 pi over 3 times e minus 1. And so that would be the triple integral that we were working with before, but switch to spherical coordinates. Okay, here's another one. So we want to perform this triple integral over the volume where the region we're integrating over is x squared plus y squared plus z squared equals 16, where z is greater than 0. We got to recognize that this is the equation of a sphere radius 4. We only want z to be positive or 0, so we only want the top half of the sphere. So here's your picture of what that region E represents. That's our box. Being that it's a sphere, it would be nice to do this in spherical coordinates. Again, it's more about what you're integrating over than the function here. So if we look at this, we say, okay, well, let's do this in spherical coordinates. We can say that rho is between 0 and 4 because it's a radius 4 sphere. Theta is this rotation here, 0 to 2 pi. And phi, I have this symbol, but we were using this symbol before, so phi is between 0 and pi halves. Why 0 and pi halves and not 0 and pi? Because we only have half of the sphere. We're only going this much of a rotation from the z-axis, so 0 to pi, halves. Right? So then we make our conversion of our function here. All right? This is our function with respect to the volume. Well, the intervals are going to be 0 to 4, 0 to 2 pi, 0 to pi halves. And so our differential is going to convert over to be rho squared sine phi d rho d theta d phi. The function is going to convert over because x is rho sine phi cosine theta. Z is rho cosine phi. Then we have the plus 3. So this is the conversion over. So it looks kind of messy, but what we're going to do is we're going to distribute this here or here to the 3 and simplify. So you see 3 rho squared sine phi here. And when I distribute this into here, these are all multiplied together, right? So we would have a rho, another rho, and a rho squared, so that's rho to the 4th. We have a sine phi and another sine phi, so sine squared phi. We have a cosine phi and a cosine theta. So that's all that is. And now we're going to integrate this thing with respect to rho first, then theta second, and then phi third. That's only because of the way we set up our integrals here. Since everything's constants, we could pick any order we want. And this looks like it might be a little tough, but just the integration actually turns out not to be that bad because we're doing one variable at a time, and we'll start with rho. All right, so what do we end up with here? If we integrate with respect to rho first, we end up with 2 rho to the 5th, and then rho cubed over here. And so that'll be our integral with respect to rho. Plug in 4 here and here, and then 0. So really just a 4, because 0 will zero everything out. And so if you plug the 4 in, 4 to the 5th times 2, it's getting big here, 2048. All sine squared phi, cosine theta, all those are just sitting there, right? Because they're just constant multiples in this case. And then here we plug in the 4, we get 64, 4 cubed sine phi. Now the next is to integrate this with respect to theta. Well, this is the only term that has a theta in it, so all this is one big constant multiple. So that times the integral of cosine theta, which is sine theta, so that's there. And then this times, this is integrating with respect to theta, so this is just one big constant, so this times theta. So 64 theta, then sine phi. So plug in 2 pi in for theta here and here, or here, sorry. Well, sine of 2 pi is 0, so that'll be gone. And then here, 2 pi in here makes this 128 pi sine phi. All right, then I'll plug 0 in here and here. Well, sine of 0 is 0, so that's all gone. And then plug 0 in here, that's 0 times this whole thing, so that's gone. So this is the only real thing that we end up with after that step. So then if we integrate that with respect to rho, we would get 128 pi times the integral of sine rho with respect to rho would be negative cosine of, no, sorry, I keep saying rho, phi, okay, of phi. This is phi, okay? And that'll go between 0 and pi halves, okay? And so we plug pi halves in here and here. So what do we end up with? Well, we have the 128 pi times, plug the pi halves in. You're going to get cosine of pi halves, which is 0, okay? And so 0 minus 128 pi times, plug in 0, you're going to get 1, so you get minus 1 here. But with the negative, we end up with 128 pi. So there's our answer. And so you see, integrating with respect to spherical coordinates made this thing, fairly doable. And that's because we were integrating over a sphere. It looked kind of messy at first, but the integration itself should have been fairly easy to follow.